Okay, so welcome back to my series on lectures for SP015, or they're more like summary lectures. This is just to guide you on your short notes. Um, we have covered kinematics. I'm just going to give a quick reminder. We have covered kinematics. We have covered momentum. So momentum. We have covered Newton's laws. And then we have covered work, energy, and power as well. So we have done all of that. Now we want to consider a very special case of motion of objects. Rather than moving separately, or rather than moving in a straight line, it's going to be moving in a circular path. So let's say something like that. Okay, so if you have a circular path like that, and your object is just moving about it or following that path, it's going to rotate about an axis. Okay. Now, if you take a line from that axis to one position of the object, okay, and then a few seconds later, it might be somewhere here, right? And again, you draw that line, another line from the center, right? That angle is what we call, so first one, angular displacement. Okay, so these we want to define a few variables before we actually apply this. We apply mathematics or physical laws or mathematical laws based on this motion. Okay, so we want to define a few variables first, and the first that we want to define is this angular displacement. Okay, generally we will have theta as the symbol to represent it, and this is going to have units of radians. Radians is just an alternative unit for degrees or rotation, right? So let me just remind you that 2 pi radians is actually equal to 360 degrees. So you should practice on using that, on doing that. Okay, now if I were to talk about how fast that object moved from A to B, then what I'm talking about is actually angular velocity. So if I take the first derivative of the angular displacement, I'll have angular velocity. Okay, the unit for this, the units will be in radians per second. So much like we have displacement and velocity, now we have angular displacement and angular velocity. Okay, now one of the interesting things when an object moves in a circular path is that eventually it will come back to its initial position. The amount of time, right? The amount of time that it takes to go back to its initial position is what we call a period. And generally we will use the symbol t for it. So period is just time to return to initial position. Again, this is just time, so it will have the units of seconds. Okay, now if I were to take the inverse of that, okay, if I were to take the inverse of period, what I'll have is what we call frequency. Okay, so this is called frequency. Rather than saying what is the time it takes to return to an initial position, we are saying in 1 second, right? How many turns can it make? Okay, so this is going to be number of rotation per unit time. That means that our unit is going to be 1 over s, or which is just s negative 1. Another unit for this is actually hertz, okay, but that is the same thing as per second, okay. So it's how many rotations per second, or how many radians per second. But this one, it has to be a complete rotation, okay. Now, at this point, it's relatively important for me to ask the question, right? What about the factor that makes the object moves in a circular path? Okay, so let's say I have an object there. 1 minute. Let's say I have an object there, and it's traveling in a circular path. It's traveling in a circular path. What forces is making it travel in a circular path? Well, whatever those forces are, depending on the situation, whatever those forces are, what we will have is what we call a centripetal force. Now, what I want you to remember is that the centripetal force is no different than the resultant force in Newton's law. Okay, so this is going to be the summation of all forces that contributes to the circular motion. Okay, generally the symbol that we'll use is FC, just to label that, okay, this is going to be towards the center. So what that means is that the centripetal force will have the same direction, okay, sorry, its direction is going to be towards the middle. So FC is going to be towards the middle. Now, this can be, in general, two cases, generally, that you'll consider. The first one being a tension, right? Tensional force. Or it can also be a normal force, okay? So these are the two cases that you need to consider, okay? Now, of course, when you have centripetal force, you will have to talk about acceleration, because Newton's law is still applicable here. Okay? Newton's law is still applicable here, where you have Fc equals to mac, okay? And this AC is actually what we call centripetal acceleration, okay? Centripetal acceleration, it means that it is the acceleration that keeps the object traveling in a circular path. That's what it means, okay? And the reason is this: in uniform circular motion, the word uniform simply means that the speed of the object doesn't change. However, in order for it to travel in a circular path, right? In order for it to travel in a circular path, its direction must change. So whilst the speed, so let me take velocity, whilst the speed of the object is 0, its velocity will not be 0. Okay, and when its velocity is not 0, then we can calculate some centripetal acceleration that causes the object to change direction. Okay, to change direction. And of course, centripetal force will have units of Newton. Okay, here centripetal acceleration will have units of meters per second per second. We'll have that. Okay. Okay, that is going to be the first part of the video. Welcome back, and we are on the second part of this video. And now what I want to do is actually, I want to apply the variables that we have defined before and to specific cases. In general, let me just change colors here. In general, what you want to apply, much like you apply Newton's law. So when you apply Newton's law in chapter 3, you'll have F equals to ma, or at least you have the summation of F equals to ma. Now, so this is chapter 3. Now in chapter 5, what you want to apply is the summation of all forces equals to the centripetal force, which is equals to MAC. So imagine if you have, so this is going to be case 1, right? So case 1, imagine if you have an object traveling in a horizontal circular motion. So you have an object, you spin it around, and it's attached to a string, right? An object that is attached to a spring, and you spin it around horizontally. So what contributes to the spinning or to the path of the object is actually tensional force or tension force. So in this particular sense, what I can say is that if I consider all the forces that is pointing towards the middle, the only one that is pointing towards the middle of the circle is actually tensional force. Now, one might argue you have weight as well, but as you can see, weight is not pointing towards the middle. You are only asking of the forces that is pointing towards the middle. That's what it means. Okay. So now what we've done here is going to be FC. This is going to be equal to FC, and FC is equals to MAC. Okay. Now what I have not done before is to define or is to tell you how to calculate AC. AC is actually V square over R. This is what makes it circular, right, or centripetal. Okay. So what that means is that I can combine these two. I'll have T equals to mv square over R. Notice that your tensional force will depend on how big your circular path is, and the mass of the object, and how fast is the object moving. Okay, so this is going to be the first case, case 1, horizontal circular motion. Okay, now you might ask, what if my object is not turning because of tensional force? There's no string, right? Let's say it's just a car, right? Let's just assume that it's a car. Well, if you take the top view of the car, let me just draw it out. Let's say you take a top view of the car. So this is the top view of the car. No. Here's the top view of the car. And then you can also have a side view of the car, right? Okay. So if I just draw a car here, here's my car. Okay. Now, if it turns, so here's my car from the top view. If it turns, that means you will turn the steering wheel to the left, right? So that means if it turns to the left, right, the frictional force is to the left as well. Okay, it's keeping it from going the other way. So if I were to apply the summation of F equals to FC equals to MAC, okay, I will find that this is actually equal to my frictional force. My frictional force is also equal to mu n, which is also equal to, I have n going upwards, and I have weight going downwards, which is just mu weight. Okay. Now, of course, I can extend this. I can extend this by saying, okay, MAC is just mv square over R, and then mu w is just mu mg, right? I can cancel the m's out. I can have v square equals to mu rg. Okay, so how fast the car can travel in that circular path depends on how rough it is, or at least what's the coefficient of friction, how big of a circle that you can make, and the gravity around it generally is going to be constant on Earth. Okay, so these are the cases that you have for horizontal circular motion. You can have either a string, so this is going to be, let me just label that now. Okay, so I can have, oh, that's big. I can have cases for string if the object is connected to a string, or I can have it in a car, both a car making a circular motion or a string being spun around, sorry, an object connected to a spring being spun around. They both can form horizontal circular motion. Okay. Okay, now what we want to consider is a vertical circular motion. Okay. Imagine if you are on a roller coaster or loop the loop, that's what they call. So a roller coaster has tracks, and those tracks can go loop the loop, right? Loop the loop. So let's just draw the path out. I can have a roller coaster. Okay. And then I can have a car being at either at the bottom or at the top. Okay, the center of the circle is over here. I can draw out the free body diagram. So if I were to say at the bottom, I can draw out the free body diagram. I can have weight going upwards, downwards, and then I can have the normal moving upwards. Okay. Now, if I were to consider all of the forces along that line, so along this line, parallel to that line, and all of the forces is going to be N minus W, and that's just going to be mv squared over r. Okay. Now what about the top? At the top, I will have weight going down and normal force also going down. That's my normal force. Now, instead of minuses, I will have N plus W equals to mv squared over r. Okay, I can do the same thing. So this is for more of a roller coaster cases. I can do the same thing again, the second part of it, if I were to just attach an object to a string. Remember, now this time I actually have a string. Okay, I have a string. So let me just draw out the string. I have the center of the circle, then I have an object, I'm going to make it round, then I have a string. Again, at the bottom, okay, I have weight going down, and then I have tensional force going up. So the summation of all the forces is equal to my tension minus my weight, which is equals to mv squared over r. At the top, I have my tension going down as well as my weight. So at the top, I will have the summation of all forces. Okay, what are the forces? I have tension, I have weight, and that is going to be equal to mv squared over r. Okay? And then whatever situation that you have, you can always just draw out the free body diagram and ask yourself what forces is pointing towards the middle or away from the middle or center of the circular path. Okay, so we have considered if the motion is horizontal, we have considered if the motion is vertical, okay, and between them it's 90 degrees. Now what we want to do is to find what happens if the motion is instead at some angle. Rather than being completely horizontal or completely vertical, we want to have some angle. So the situation that we have is going to be a conical pendulum. A conical pendulum is not like a pendulum where you just go left and right. That's not what you have. A conical pendulum rather will spin, so it will rotate. It will follow this path. Okay, this is the path that it will take. It will form, the object itself will form a horizontal circle. It will form a circular So it will form a horizontal circle. However, as you can see, the tension, okay, the tension is not towards the middle, rather it is at an angle from the middle. Okay, so let's just call this a ceiling. So there is some angle that is related to it. I can keep on drawing the force diagram. I can have weight going downwards. So if this is the case, then our FC must be towards the middle. I will have to resolve T into its components. So if I were to resolve T, I will have two other forces. I will have going up, this is going, let's call it Ty, and then I have Tx, which is towards the middle. So Tx is towards the middle. Okay. So I can say the summation of F, which gives me Fc in the direction of towards the middle, I will have Tx, which is just T sine theta. Okay. But of course, I won't be able to find out what T is or Tx is if I don't have Ty. Here I can apply Newton's law, summation of F in the y direction. In the y direction, it's going to be in the centripetal force, the x. In Fy, I have Ty minus W, which is equals to 0. So my Ty, which is T cos theta, okay, then I'll have T cos theta equals to W. Okay, so here I can rearrange this to have T equals to W over cos theta. I can take this and put it in here. What I'm left with is my Fc equals to mv squared over r. That's fine. And then I have T sine theta, but now T is being removed. I'll have W cos theta, then I have sine theta. Now cos and sine, sine over cos just give me tangent. So I'm left with mv squared over r equals to W tangent theta. Okay. Then I can figure out what's the velocity by just rearranging that. I can have v squared equals to, so W is just mg tan theta. I can cancel out the m. I'm left with rg tan theta. I can figure out the velocity. So gr tan theta square rooted. So that's the velocity. So that is the case for conical pendulum. It is where it is not fully horizontal and it is not fully vertical. Okay.